periodic properties. Goal number 2, atomic radii. We learnt the introduction and two important terms in a special way. First was screening effect, and the second was effective nuclear charge. With the help of these terms, we will start discussing the periodic properties. The first periodic property is the atomic radii. Definition of the atomic radius is the distance between the center nucleus and valence electron. So, from the center of nucleus to valence electron, the area is known as atomic radii. It is measured in nanometers, which is 10 to the power of minus 9 meters, or in picometers, which is 10 to the power of minus 12 meters, and the most used one is angstrom, which is 10 to the power of minus 10 meters. These are the units which are used to measure atomic radii. Now, based on the nature of atom, we have different radii. First is covalent radii, in which we have two types, that are homodiatomic and heterodiatomic. In homodiatomic, the molecule is made up of two atoms which have the same electronegativity, so the atomic radius is measured as 1/2 of the distance from the center of the two nucleus. This is the covalent radii for homodiatomic molecules. It is very easy to calculate the distance between two similar atoms. That is, radius of A plus radius of another A, which is equal to 2RA. In case the molecules are heteroatomic, that is, if the molecules are made up of less difference in the electronegativity, then the distance is AB, which is equal to radius of A plus radius of B. This is how we can get distance. In this, also we can see that the distance is 1/2 of the center of two nucleus. This is 1 and the second one is little bigger. So this is the covalent radii. Suppose we have heteroatoms with electronegativity differences. Then we have different formula, which is dA minus B, which is equal to RA plus RB minus 0.09 multiplied by XA minus XB whole bracket, where XA is equal to electronegativity of A and XB is equal to electronegativity of B. This is one way of calculating the atomic radii. Next is the van der Waals radii. This is similar to the previous one, but here we will see internuclear distance between two molecules. We will take an example A and B here, and another A and B molecules here. Now, these are two molecules and we will take their center as the internuclear distance, which gives us van der Waals radii. This is mainly used for nonmetals. Now we'll move on to the third one, which is metallic radii or crystal radii. We will draw a diagram. Here we have a metal surface in which the atoms are arranged in this manner, that is, they are closely packed. So, when we talk about the van der Waals radii, it is only between the two molecules, but in case of metallic radii or crystal radii, the distance is between two atoms in a closely packed surface. We will take it from the center of two molecules which are closely packed. That is, half the distance of that, and it is known as crystal radii or metallic radii. This is only useful or valid for those atoms which are closely packed in the surface. In this way, we understand that atomic radii is nothing but the distance of the center of nucleus and valence electrons. We also saw the various types of atomic radii, which are covalent radii, van der Waals radii, and metallic radii or crystal radii. In goal number 3, we will see what happens to the atomic radii when we move across or a long period or down the group.